So let's talk about a couple of the problems on the assignment I just gave back.
I'm not going to be working here. I'm at lab in Diego.
What?
You're the lab in behind me.
Okay, so the first one was question number 14, okay? Which for the most part went, okay. So here's the deal. The whole key to this problem is understanding what that battery is going to mean in terms of which direction the current's going to flow. So when you close this switch, is this side, is the long dash, is that the positive terminal of the battery or the negative terminal?
Positive.
That's your positive. So in the traditional idea of the current's going to flow from this side out and around, okay? So this isn't so much, it's magnetic theory, but it's also you understand circuit diagrams. So when it gets to this bottom loop, okay, take your right hand, the current's going to be going this way, and so that magnetic field is going to be going up. So in the plane of the top loop, that magnetic field is going to be coming up. So within the top plane of this, you're going to be having dots, okay? And you're going to have an increase in those dots, right? So if you're getting an increase in the dots, what's Mother Nature going to do?
Make X's.
Make X's. So then Mother Nature is going to send the current in this direction, like this, to make X's. So this current then, in the top loop, is going to be going in a clockwise direction. Okay? And that boils down to understanding what this switch means. Okay? Now, let's talk about 15. So number 15, here's this loop, okay? And you've got the north end of the magnet, and it's going to be moving up into the loop, okay? It's going to be moving up into the loop. It's going to be key. So which direction, since this is the north end, are the field lines emanating from the north end or coming into the north end? Emanating. So they're going to be like coming up like this, right? So imagine this. Here's your loop. Here's the north end of a magnet, okay? And you're going to be going like this. So when it does that, so in the plane of this loop, what's it going to sense? Dots or X's?
Dots.
Dots. So what's it going to do?
X's.
It's going to create X's, okay? So the only way that you can make X's then is if you curl your hand in this direction and wrap your fingers in, okay? So this one is also going to be going in a clockwise direction, okay? Now, in terms of the force, I gave you some leniency. If you kind of took down anything, I didn't take off the point. But let's talk about the direction of the force. So you got to use the right-hand rule again. So once you establish the fact that the current is going to be going around like this. So this is the current in this loop. It's going to be coming around like this. So the current's going to be coming like this. The magnetic field is coming out this way. So the force on the wire is going to act to try and pull that thing inward. So that force is going to try and compress that spring, that wire, and make it actually try and collapse itself. Now, if you pull that north end of that magnet back out, okay? So if you're like this and you pull the north end of the magnet out, what's it then is Mother Nature is going to sense a decrease in dots. So it's going to make
Dots.
So the only way that you can make dots then if the current then is going to be going in this direction, it's going to be going up. Then that situation, the force is going to be trying to expand it out. So if you move that magnet in and out, that wire is going to be going back and forth like this. Okay? Got that visual. All right, so let's see that in action. So let's go back to the room. So this is the old style light bulb. And you have two settings. And you kind of got to get close enough where you can kind of see what's going to happen with this deal. So what this is if you look on this, it's a very, 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 very fine nichrome loop that comes up, makes a loop, goes around kind of a figure eight and back down. So this is unique because I can actually run this thing on two different settings. I can run it on a DC, which stands for direct current, or I can run it on AC, which is alternating current. So how this works, and this is the old style way of making light. So if you turn that on the DC side, and if you put your hand here right away, it feels really, really warm. So what's happening to produce this light, and this is why these bulbs are so highly inefficient, they didn't last very long. Because basically what you're doing is you're taking a wire and you're forcing this electricity through it. And it doesn't like it, so it heats up, okay? So in the process of heating up, you're taking all of these electrons that are going, oh my God, this sucks, right? And it jumps out of its ground state, and it doesn't like that either. It comes back down and emits a photon, okay? So this is happening billions upon billions upon billions of times, right? And in the process, not only are you producing visible light, you're also generating a tremendous amount of heat, okay? So literally, instantaneously, when you turn this on here, thermo, okay, put your hand there, right? Right? So it gets warm pretty fast. So what would happen is that these filaments tended not to last very long because what would happen is they would erode, and then they would get smaller and smaller and smaller, and they would eventually just break. So I'm going to have it on the DC side, so I'm going to put it on there, and then I'm going to take this magnet, and I'm going to bring it closer. I need a stronger magnet. Hand me, where's one? Hand me that one.
Did we get dimmer my blind?
It shouldn't really.
Oh, well, blind.
Okay. So now with this one you can see that deflection. See that filament pull towards that magnet? Here, let me turn it to the video audience. Okay?
Oh, yeah.
Oh, wow.
Okay? And then I can do it with that one. So with that one, you have that interaction with that field. So this is an interaction of two magnetic fields. So obviously there is a force acting on that wire because of the fact that when I bring this magnet closer to it, it's pulled towards it. Now, in that situation, it's a DC. That current is only going in one direction. Now, I'm going to switch it over to the AC side. On the AC side, it looks the exact same. Okay? Still looks like it's the same amount of light. But now with the AC, that operates like on 60 cycles per second. So now I'm going to bring the magnet by it, but now, here's the deal. Now that current's going back and forth, right? So it doesn't know what to do, like back and forth, back and forth, back and forth. So now when I bring this close,
What?
okay, see how that vibrates very, very rapidly?
Oh, it's vibrating?
Yes.
I thought I was just blind.
Yeah.
Yeah, I was like,
Okay?
weird.
So, oh yeah, it's getting us hot. Okay?
You just put your hand on it?
Well, no, you just put it there.
I know, it
So,
would have been funny.
here's the deal. So if you're on the DC side, where that current's only going in one direction, it only pulls it towards one side. But when you switch it over to the AC side, then,
My eyes.
because that's vibrating at 60 cycles per second, that's why it looks like it's going back and forth like that. Now, we're going to kind of combine some things in one.
My vision's
It's
fine.
not even
Oh, I know.
as good as
It's getting
getting
trash.
It's just a spot.
Dude, 60 hertz, no wonder it gives me a headache.
144 hertz.
Dude, if it's 144 hertz or bust. Sorry, 60 hertz is too slow. It's not enough. I
Okay,
know.
so this is going to take some teamwork. All right. Where is,
I don't know if I can justify 240 though.
okay,
Is that a thing?
Yeah?
so I'm going to turn this on. You bring that close.
Me?
Yes.
Oh, okay.
It's not like my
Okay.
son's even gonna want it.
Yeah.
Anyway.
Hold on, not yet.
That's it. Mine's not bad.
No, not the strobe light.
Epilepsy.
I literally, it's funny because they literally thought I had a mini seizure a few
Okay,
days ago.
so now
But I was
bring
like,
that close.
no, stroke, not seizure.
Okay.
That's not good.
It's whatever.
No, now I can really
No.
see it.
Well,
Am I supposed to be saying something?
We had it
no, 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 no.
I just smashed it.
No. Well, it's not. I should be able to, hold on.
Matches.
If I hit it just right, it'll hit her stationary. That's pretty close. So what's happening is that strobe light is flashing like at every point that it's in the same location.
Oh, poor Amanda's looking straight into it.
I think it should be like 30 hertz.
Blind is
If it's 60,
Yeah,
Yeah.
kind of, it's not working as well as it should. Okay, all right, that was what was supposed to happen. So,
Well, but
all right,
the
kids.
film
just
is
keep
emitting a
this for
light. You're
safekeeping.
always gonna-
Yeah, huh?
You got like a spot on your face.
Okay,
Put a question.
all right, back we go.
Touch the hot.
Oh, no, no, put it on that one, don't put it on that one.
I didn't put it on there.
Yes, sir, I was afraid it was gonna happen.
No, I was trying to put it so that that was at that end.
It's not that hot.
16. He's so smart. My parents are just gonna
All
be
right.
lucky if he graduates.
So this is a continuation of the lab that you all did yesterday, where you were just looking at the forces side of it. And now we're going to look at the magnetic side of it, okay? So here's what you're going to do is that I'm going to tell you, it's like, okay, here's the procedure so that we're all getting kind of the same data. The basic idea is this, is that if you have a loop, okay, and what we're going to do is we're going to view those plates as basically an infinite number of loops like this, okay? So imagine that here's this loop, right? Here's this loop. Let's just start with this idea. That instead of an infinite number, we're just going to start with one simple loop, okay? And we're going to attach it to a cart, and we're going to send this cart into a magnetic field like this, okay? So now if you were to do this, okay, so imagine this. I physically want to build this where this thing is going to go through in this loop. So I want magnetic lines going like this. So would I have the north end of my magnet here, or would I have the south end of my magnet here? So I want to generate a magnetic field that's going into
North.
the plane of this board.
So it'd be north basically.
Yeah, so I want so imagine this. I'd have the north end of my magnet here, which is creating a magnetic field going in, because those magnetic field lines are going to start at the north and they're going to go out this way. So imagine now I'm going to send this wire like this, okay? So as this wire hits that magnetic field, what is the wire going to sense?
Change in field.
Yes. So it's going to sense an increase in what?
X's.
X's. So it senses an increase of X's, so what's it going to do? It's going to make O's. So which direction is the current going to flow in the wire to make O's? Why, Gannon?
because if it goes right, it'll become an out.
So I want to look at what's going to happen on this leading edge. So when this leading edge hits this, okay, when it hits this, what's going to happen?
The current's gonna travel off.
Current's going to be going down, or the current going to be going up?
Up.
Current's going to be going up. Why?
Because it forces current out of the plane.
Okay, so I'm going to be looking at this side over here. So this current's, so the wire's going to be coming like this, right? You got to have this visual. This wire is going to be coming like this, and it's going to sense this increase in X's. So it's got to do what? It's got to make dots. So to make dots coming out, right? So current's going to be going up, right? And then over here, this is the region that I want dots, okay? So is the current be going up, or is the current going to be going down? Down, because I want that current to be going down, so that way on this side over here, I'm making dots. Okay, so when this loop, I lost my loop, there's my loop. So when this loop hits the X's, it needs to make dots, so it's going to send that current down, so that in this region over here, I've got a magnetic field coming out, okay? So the current's going to be going down, okay? Now, because that's going to make dots over here. Go with this. Now we need to use the right-hand rule to figure out the force that's going to be created on that wire. So the current's going to be going down like this, right? The external magnetic field is doing what? Going into the page. So the force on the wire is going to be going,
Wait.
current's going down, magnetic field is going in, so the force is going to be going right. So if this part is going in this direction, the force on it is going to be going,
The opposite.
so what's it going to do?
Slow down.
Well, it's going to slow it down. Okay? So this is why when you push that cart through, it acted as a brake. Because it's going to induce a current that's going to work in opposition to the changes in the magnetic field. So, now, if the force acted, if you did this and the force acted in that same direction, what would it do?
Speed up.
Then it would speed it up, okay? So in this thought process, and this is what you've got to think through on one of the last questions on the lab, is that visualize this. You're going to have like the sheet of metal. But imagine that you have an infinite number of individual wires that are going to be subjected to that changing magnetic field, okay? I did a simple example when it's just one. But this is how you have to visualize what's going to happen with these wires, or with that metal. It's all going to be an infinite number of small wires that are going to be continuously being subjected to the same changing magnetic field. Okay, got that visual. Okay, so let's go to the back and we'll actually go through the lab and what I want done.
I don't know if I can do it.
I got it. Okay, so here's what you're going to do. So I'm going to make sure, we're going to make sure everybody's kind of doing the same gig as far as the procedure goes. So you're going to start with, actually I'm going to flip this over. It doesn't make any difference. We'll follow the procedures. So the length of this is 40 centimeters. So we're going to start this at 50. So you're going to put the leading edge of the cart at the 50 centimeter mark. And then you're going to let go, and you're going to let it go until the front edge hits the 10 centimeter mark. Okay? So you're here, boom, start it, stop it when it gets to that point. And you're going to do that like 5 trials, okay? Easy peasy, here you go. You're going to take the average time. Then you want to calculate an experimental acceleration. So, Adeline, we're clever. What are we going to let the initial velocity be?
0.
0?
Yeah.
Okay. Now, we're going to start at 50, and we're going to end up at 10. So what else are we going to know? We're going to know displacement. Oh, position final minus position initial. Oh, so we're going to know how far it's going to go. What else are we going to know?
You have no time.
We're no time, right? And we know distance equals 1/2 at squared plus v naught time. Adeline said we're clever, so the initial velocity is 0, so that drops out. So we're going to know a distance, we're going to know a time, we can calculate an acceleration. Okay, so you can do that 5 times. So up here to the top, it's going to ask for the angle. Let me know if your phone doesn't have the app or if somebody's phone doesn't have the app. Let me know. I'll bring over my phone. We're going to get an exact angle. You're going to find the weight of the cart. Okay, take a Newton scale. So help me if you ask me how to do that. I'm just going to flunk you. Okay, and if you ask me how do we get the mass? Again, I'm going to flunk you if you ask me that question. I swear to you, I will. So then we want to determine the force acting to cause the cart to accelerate downward. Okay, so we're going to find the value of that cart. And then, because this is a frictional surface, it's going to be your net force. And I tell you up at the top, so that everybody's on the same system, I'm going to define anything acting down as being a negative value. Okay, anything acting down is going to be a negative value. Okay, so then you're going to calculate a theoretical acceleration, and then you're going to actually calculate the acceleration based upon the data. Okay? Then, on the next set, you're going to place the magnet, like so that right when it starts, it's like this. Okay? So you're going to be like this. And then you're going to do this. So the reason that we did the 50 to 10, because that's the length of this. So that way when it gets down here to the 10 centimeter mark, that's when that magnet is leaving that plane. So that magnet is acting as a dampening force the entire length that it's there. So then you're going to measure these times, and then you're going to get that acceleration. Okay? So you're going to have an acceleration, you're going to have 3 different accelerations. You can have a theoretical acceleration based upon force parallel and mass. You're going to have a measured experimental acceleration without the magnet, and then you're going to have another acceleration with the magnet in it. Okay? So, over on the back side, okay, that's basically what we're going to do is I'm going to take you through these calculations. So, what you're ultimately trying to find is the opposing force created by that magnet. Okay? That's your end game. So you're going to know what the downward force is, you're going to know what your net force is, you're going to find the opposing force. Then, when you get to number 9, I'm going to tell you, hey, this is the magnetic field strength, 8.0 milliteslas. I'm going to give you the length that was in the magnetic field, which is 5 centimeters, and then from that, you're going to try and calculate the induced current. When you get to question number 10, you have to have this visual, okay, about what's happening on number 10. I tried to write it out in words, but here's what's going to happen. Is that assuming that you're back here, okay? So I'm looking at the back of the cart, all right? I'm looking at the back of the cart. And then I tell you that the left side of the magnet is the North Pole. So here's the magnet. This side here is the North Pole. So are field lines coming out or are field lines going in the left side? Out. So visualize this. This thing is going in. That's the North Pole. So from the outside perspective, you're going to see field lines that are emanating out from that North Pole. So what you want to do then is figuring out, okay, what's Mother Nature going to do within the plane of this metal to deal with it passing through the North Pole of that magnet. So what I tried to do on this diagram, so what I did is I put this little blue line right here. So what I'm saying is that this is one wire in this loop, okay? This is the leading edge of an infinite number, and I picked that one. So when I have that box that says current, I'm not saying that's the direction of the current. What I want you to do is on that line, tell me which direction is the current flowing. Is the current flowing up, or is the current going up, or is the current going down? That's what I mean by that. So it was tough to kind of convey that. So what you want to do is put X's or dots, and then indicate if the current is making more dots or more X's, and then the direction of the current. So you're going to tell me, are you making more X's or are you making more dots? Based upon that idea, what's going to be the direction of the current? Okay? And it's going to be what's happening behind that line, not in front of it. What's happening when it reaches that point. Now, when you get to the question about the solenoid, so let's go back up to the front right quick, and then I'll turn you loose. Okay, so on the questions about the serendipitous solenoid, here's the visual. So this is actually data off of this. So what's going to happen is that to collect this data, and this is what I actually did, I took a magnet like this, and I used this solenoid. So what I've given you is the voltage. So when you pull this thing out, okay, you get a measured voltage of 0.8. So here's what's important. This is the north end of the magnet that's inside the solenoid. I'm going to pull the magnet out, okay? I'm pulling the magnet out, okay? And when I do that, I measure a voltage of 0.80. That's actually what you get on your voltmeter, okay? So that's going to be 0.80. You're going to know that value. I've given you the diameter of this cross section, okay? And what you want to find is first the rate of change in the magnetic field per unit of time, and then tell me what's the direction of the induced current within that solenoid. So is that current in there going to be moving in a clockwise, or is it going to be moving in a counterclockwise direction? Okay, I'm done. We'll go from here.
Or can I use the restroom?
Yeah.